And I'll tell you a few, let's just do a few measurements. So we can do ordinary least squares, right? So that's you've done this a million times, I'm sure, but it's a simple thing. Wow, the sadness. Okay, these have to be eliminated. Okay, so here's the thing. With ordinary least squares, we've got some y, we've got x, we've got some dots. And what you do there is you assume error is in this direction. Right, this is a very important aspect of this thing. You can regress x on y, and when you do that, you assume the error is in this direction. Now, it may be that you really have errors in both, right? And that's often the case for things. So then you kind of want to assume some sort of error ball for both of them. And that's a different mathematical thing. You may be able to characterize the error in some way, so then you take that into account. You may have no idea, and there are different treatments for that. So I just wanted to, it's called major axis regression. There are different kinds of, or reduced major axis regression. I want to show you this. It's quite a beautiful thing. So it's a little bit of a detour. But we would certainly, if this is mass and this is something like metabolism, mass we can measure well, right? So we're going to be happy about that. Metabolism, much messier. So it's going to fit into classic regression. Okay, well, is that true? Okay, ordinary least squares is a good thing. So standardized, I guess it's now called standardized major axis linear regression. So that's what you do if we don't know what the errors are, right? So it's just a big mess. And I want to point you to, wow. So Samuelson, who's a famous economist, has this 1942 thing that I would point you to. And then there is a paper here, Rayner. This is great too. This is from zoology, right? Completely different worlds, right? But this is all about regression and thinking about the different kinds and connecting them in cool ways. So, but let me just show you some of that. RMA, right. And it turns out that this is really this is a surprising thing. It's just this, so we're going to have this, if we take this set of data and we look at the distribution of y, maybe it's like this, whatever it is. Messy thing, right? So we're going to take all of these points and then make a histogram. Like ignore x and make a histogram for y and a histogram for x. There's some standard deviation for this thing, and there's some standard deviation for this one. That's sort of the typical width of this, So the crazy thing is that you actually just, to find the slope of best fit using RMA is it's just this standard deviation divided by this standard deviation. And there's a very nice thing where you can connect it to the slopes you get from normal regression. It's just multiplying this slope by the correlation coefficient or dividing by it, right? So there's some details we could go in. So if the correlation coefficient is 1, right, we've got a beautiful thing, then all of those things match, right? Y regressed on x, x regressed on y, and this one that's in between, they're all the same. Makes sense. So that's in here too, I think. It's the only linear regression that's scale invariant, and that seems unbelievably important, right? And that's what, right, that's weird, right? So that's what Samuelson was thinking about. It says, these things this slope shouldn't matter what the units are, and apparently it does. So Samuelson, and of course, independently discovered by others, which is the, what's it again? Stigler's law, right? That yeah. You discover something for the first time, it will not be named after you. So, including Stigler's law. Right. Okay, so this is kind of a beautiful thing. So if you're messing around with this sort of stuff, this is something to know about. Really good. And let me get the Rayner one. Yeah, again, one of these things. So I won't go into too much, but this is kind of giving you this idea about the different kinds of errors. So this is exactly the thing I was talking about. What's weird, actually, is if you do this regression on just a cloud of points, it will tell you right? You'll still have a standard deviation. It will say that it will give you a slope for that, right? You've got a box of just static noise. The RMA one will just say, okay, divide this standard deviation by this one, that's the slope for it. Because the correlation coefficient is 0 in that case, then you'll get the right thing. You'll get that the slope's infinite and 0, depending on how you regress. Anyway, this is an old paper now, but it's nicely done. There's some good mathematical work connecting all of these things, right? And that's sort of the key thing in here is here's the slope, or the correlation coefficient is connected to these standard deviations. Maybe I said the wrong thing. This is kind of the plot I wanted to get to, right? So here are these different things, right? This is y regressed on x. That's x regressed on y. Is that? Right? This is where you have a conception of error. Here and here, there are ones where you want the line such that, and this is major axis, such that the distance to that line from every point perpendicularly, which sort of should make sense, is as small as possible. I'm not sure what that one is. This is where you want to minimize the area of that triangle. That's what this regression does. So it's groovy, very groovy. I like that a lot. Okay, so that's cool. And this is the thing where the slope, ordinary least squares, y on x, x on y, they're connected by the correlation coefficient, by that factor. It's cool.